Well, welcome to the first section of Chapter 8. This is 8.1, Simple Trigonometric Equations. And today the objective will be to solve simple trigonometric equations and to apply them. Now, it's really easy to solve a trigonometric equation. It's just a little simple algebra and some trigonometry. Applying them, I'm going to take you on a journey at the end of this lesson, and I want you to take on this journey like a challenge. We're going to do a really cool graph, and it is really a great example of an application of trigonometric equations. There's also a couple key concepts like angle of inclination today, and using that to define slope and things. So this is just a really great start to Chapter 8, and I hope you enjoy it. So, first of all, there are blank solutions to sine of x equals 0.5. Well, you guys, I hope you can visualize the graph of y equals sine of x in your head right now. All right, there's one we used previously, and remember, sine is periodic. It has an amplitude of 1, so it oscillates between -1 and +1. And this pattern just goes forever in both directions, making a sine wave a very powerful tool to collect data on things that occur in nature periodically. Right? Anyway, so when does sine have an output of 1/2? Well, you see 2 points on my graph right there where sine does have an output of 1/2, and you have the tools already to find the exact inputs or the exact angle in which sine has an output of 1/2. All right, so your calculator, by the way, will only give you an answer in the restricted domain of sine, and that answer will most likely be an approximation. And remember, sine is not 1-to-1, therefore it does not have an inverse. So when we're solving things using inverse sine, we have to think about the restricted domain of sine to make it 1-to-1. And that restricted domain would be the largest x interval in which sine is 1-to-1, and that interval has to contain quadrant 1, which would be from 0 to pi/2. So I see the restricted domain of sine, so I can have an inverse to be from -pi/2 to +pi/2 inclusive. Now, remember our unit circle and our key angles in quadrant 1? All right, so we have 0 radians, pi/6 radians, pi/4 radians, pi/3 radians, and pi/2 radians. And that's not a perfect diagram, but you guys remember the pattern here. Now we're talking about sine, all right? And remember, sine measures vertical distance from the x-axis at these terminal points right here at the end of these terminal rays. So there they are. Now I am hoping right now you know each of these vertical distances and you know exact answers. For instance, sine of 0 would be 0. Sine of pi/6, well, that's a 1/2. Sine of pi/4, well, that's a √2/2. Sine of pi/3, that's a √3/2. And then sine of pi/2 is exactly 1 unit. So there you have it right there. So right now we have one angle, this angle right here, which is pi/6, for which sine of pi/6 will give us an output of 1/2. So I know that this input right here, this angle would be pi/6. All right. Then you have to think, okay, in what other quadrant is sine positive? And that would be quadrant 2, again, because sine measures vertical distance. So this pi/6 happens to be a reference angle for the angle in quadrant 2, which is nothing more than a reflection of this terminal ray in the x-axis to give me this angle right here. And what is that angle right there? Well, think about that, okay? This is pi/6, 2 pi/6, 3 pi over 6, then I'd have a 4 pi over 6. That's a 5 pi over 6 right there. So guess what? The angle or the input of this point right here, 5 pi over 6. And there's 2 exact answers. Now, how many solutions does this simple trigonometric equation sine of x equals 0.5 have? Well, we found 2 of them, and that would be x equals pi over 6 and x equals 5 pi over 6. But if you just look at this picture right now, when does sine have an output of 0.5? Okay, that's only 2 particular solutions. And look at this horizontal line at y equals 1/2 or 0.5 right there. And that goes on forever and ever in both directions, telling me that there are infinitely many solutions to sine of x equals 0.5. So I have expressed 2 particular solutions right here. How do we express all of them? Well, you think about the period of sine, and we all know that sine has a period of 2 pi. All right, so then all I need to do is add multiples of 2 pi to each of these solutions, one in quadrant 1 and one in quadrant 2, and we write this like this: x can equal pi over 6 plus 2n pi, and x can equal 5 over 6 plus 2n pi. All right, now n is any integer, so that will take me in both a positive direction or a negative direction, and this represents every possible solution for the simple trigonometric equation sine of x equals 0.5. So when you do these problems, you need to know, do they want every solution? The answer would be down here. Or did they give you an interval for which they want you to find a few particular solutions? And then your answers will look more like this up here. Okay, now again, particular solutions versus general solutions. Know the difference. Okay, now find the values of x between 0 and 2 pi. So they're looking for particular solutions this time, for which sine of x equals 0.6. Now, 0.6 is not one of our key outputs on the unit circle, like we saw with the 0, 1/2, root 2 over 2, root 3 over 2, and 1. All right, so that tells me that at this point, we could find this just using our calculator and doing an approximation. All right, so if I'm going to solve this simple trigonometric equation, sine of x equals 0.6, with a calculator, all I'm going to do is I have to undo this function sine, so I'm going to take the inverse sine of both sides. Okay, so here's my original equation, but we're going to go inverse sine on the left and inverse sine on the right. Now, why do we do that? Because inverse sine of sine, well, inverse functions undo each other, which would leave me only this x, and x is going to be, this is an exact answer right here. The angle whose sine is 0.6, but we can now approximate that on a calculator. So let's get our calculator out and go x is approximately, all right, and a couple other pointers I need to give you right here. What mode do I need to be in? Well, look at the interval they gave us, 0 to 2 pi. Those are radians, so we know we need to be in radian mode. So I'm going to get out my calculator, and make sure you get out your calculator and punch this out with me. All right, second quit, cleared my screen. Mode, I'm in radian mode. How about you? So let's go second quit. We're all in radian mode, and let's punch out inverse sine of 0.6. Second sine for the inverse sine of 0.6. And to 4 sig digs, I'm getting 0.6435. And there is my approximation, 0.6435 radians. All right. Now, is that the only angle between 0 and 2 pi for which the simple trigonometric function sine of x equals 0.6 is true? You guys know better than that. All right, that's just our reference angle. That is our quadrant 1 angle. So let's go back to our unit circle. And, this does not have to be exact, but let's throw a quadrant 1 angle into this picture, and we're going to tell the world that that is 0.6435 radians. Now you think to yourself, in what other quadrant is sine positive? And of course, sine measures this vertical distance right here. All right, so sine would also be positive in quadrant 2. So a quadrant 2 angle also satisfies the above equation. So let's take this terminal ray and reflect it in the y-axis to get our quadrant 2 angle right there. Now, how are we going to get our approximation for this angle? Well, we know this acute angle is 0.6435 radians, so wouldn't this angle be pi minus that 0.6435 radians? So here it is right here. So x is going to be pi minus 0.6435. And make sure you see how we did that. 1/2 revolution would be pi, and then take away the 0.6435 radians, and you have that angle right there, which is approximately, so let's punch this out, second pi minus 0.6435, 0.6435, and there we have it. And I probably stick the 4 sig digs again, so I probably did something like 2.498. I went actually to 4 decimal places. Okay, so 2.4981. All right, so now let's see. Find the values of x between 0 and 2 pi for which sine of x equals 0.6. Well, those would be my only 2 solutions, my quadrant 1 solution and my quadrant 2 solution. So we are done with this problem. Okay, right on. Okay, now, look at the difference here. Find all values of x for which sine of x equals 0.6. Well, we've already done all the work. So now it's a simple, how do we represent all possible solutions? Well, here's what we had from the previous slide. And so I can take these 2 answers, my reference angle, x is approximately 0.6435. But then don't I add any multiple of 2 pi to that? Plus 2m pi. And then my quadrant 2 angle right there, which is x is approximately 2.4981. And let's add any multiple of 2 pi to that. Plus 2m pi. Now notice my comment in black. I'm going to tell you that this n is any integer. And that is implied. So you don't have, if you're using an n like this, we all know you're talking about any possible integer. Dot, 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 -2, -1, 0, 1, 2, dot, dot, dot. All right. But I want to put this in here for instruction right now. Okay. Now, so let's play with this a little bit. To the nearest 1/10 of a degree, so we're going to use our calculator, solve 3 cosine of theta plus 9 equals 7 for 0 degrees is less than or equal to theta, and theta is less than or equal to 360 degrees. If I had written this problem, I probably would have just said less than 360 degrees right there, because we've already represented that terminal ray with a 0, but so be it. Okay, anyway, well, solving simple trigonometric equations, this is nothing more than algebra to begin with. So let's take this trigonometric equation right here, and let's solve first for the trig function. So we need to get rid of the plus 9. So how about we subtract 9 from both sides to get 3 cosine of theta equals 7 minus 9, -2. Now, let's divide by 3. So cosine of theta equals -2/3. And now we get our calculator out, because to undo this cosine, we're going to have to do inverse cosine of both sides. So theta then would equal inverse cosine of -2/3. And that's my exact answer right there. But we're going to punch this out on our calculator to get an approximation. So theta is approximately, all right, and now don't forget, weren't we in radian mode for the previous problem? And now look at the interval here. we're talking about degrees. 360 degrees is 1 revolution. So let's go to mode and go from radians to degrees. Okay, and then second quit, and let's punch out our inverse cosine of negative 2/3. Second cosine for the inverse cosine of negative 2 divided by 3. Close my parenthesis, and I'm getting 131.8103149. And did they tell us what to round to? Yeah, the nearest tenth of a degree. So how about we call that 131.8 degrees? Now, 131.8 degrees, wouldn't that be in quadrant 2? About right there. Now, let's see. We're talking cosine, right? And cosine measures this horizontal distance right here. All right? So, in what other quadrant is cosine negative? Well, that would be a quadrant 3 angle. All right? So let's take this terminal ray and reflect it in the x-axis to get this terminal ray right here. And now, how are we going to approximate that? Well, I would probably go 360 degrees minus 131.8 degrees to get back there. So let's see if that's what I did. Yeah, 360 degrees minus 131.8 degrees. So let's go 360 minus, and I'll just go my last answer. Second answer, and I'm getting 228.2 degrees. Let's see how we did here. 228.2 degrees. And since they gave me the closed interval from 0 to 360 degrees, I know that those two are my only two solutions, and we are done with another problem. So this is how we solve simple trigonometric equations. And this is the core to today's lesson. Okay? Take a simple trigonometric trig equation, solve for the trig function, and then solve for your angle theta. Or they might have given you it in terms of x, either way. All right, so now our next core concept today will be the inclination of a line. And the inclination of a line, like the one I have shown here, is the angle alpha, where 0 degrees is less than or equal to alpha, and alpha is less than or equal to 180 degrees. That is measured from the positive x-axis to the line. So, you guys see this line in the plane? And this positive angle right here, which I'm going to say looks like it's approximately, I don't know, 35 or 45 degrees. So I'm going to call that approximately 35 degrees right there. This is the angle of inclination of this line 1 right here. And that's all there is to it. And remember, an angle of inclination has to be in the closed interval from 0 to 180. All right? So, let's talk about this. Okay? Slope of that line. What is the slope of that line? Well, you guys go on back to Algebra 1 and you know slope is. Let's throw a slope triangle into this picture. Oh, look at that triangle right there. And isn't slope rise over run? Do you see, to get from this point, the x-intercept, to this point right here, I'm going to rise and run, which I happen to see the rise right here in my slope triangle, and my run right here. Okay, now think about that. Think about right triangle trigonometry. Isn't this rise the opposite of this 35-degree angle? And isn't this run adjacent to this 35-degree angle? And you SOHCAHTOA people, isn't tangent opposite to adjacent? So that tells me that, see that 35 degrees, our angle of inclination? Well, tangent of 35 degrees would have to equal my slope. So let's punch out tangent of 35 degrees. And again, we are in degrees already from the last problem, so let's just go tangent of 35 degrees. And I'm getting approximately 0.7 or 7/10. Okay, so it looks like I want this one in 4 sig digs right here. So let's go 0.7002. And there it is right there. Now I'd call that 7/10 so I could really see it. So to get from this point to this point, I I am rising 7 and I am running 10 approximately. Okay, so that leads to a very important definition. Oh, look at that, even a theorem. For any line with slope m and angle and inclination alpha, like we just saw on the previous slide, slope will always equal tangent of alpha, my angle of inclination, as long as that angle of inclination is not 90 degrees. And obviously, our angle of inclination can't be not 90 degrees, because if we have a 90-degree angle like this right here, that means my line would be vertical and it would have no slope. So if alpha is 90 degrees, then the line has no slope. The line is vertical. All right. So we're going to get some mileage out of this theorem. Trust me. Okay, so here's what these problems will look like then. To the nearest tenth of a degree, find the inclination of 2x plus 5y equals 15. So from our last theorem, we need slope. Okay, so what I would do then is I would find the slope of this line that is in standard form right now. So how about we solve for y? So let's subtract the 2x from both sides to get 5y equals negative 2x plus 15. And then let's divide every term by 5 to get y equals negative 2/5 x plus 3. And I hope you all see that our slope is negative 2/5. Okay? So slope has to equal tangent of alpha. So negative 2/5 has to equal tangent of our angle of inclination. And how do we solve for that alpha? Well, we're going to have to go inverse tangent. So alpha equals inverse tangent of negative 2/5. All right, and there's my exact answer right there. And down the road, I'm going to show you how to get an exact answer without your calculator. For right now, we're really practicing with our calculators here. So let's all punch this out. And what mode do I need to be in? I always look at the problem. Oh, to the nearest tenth of a degree. So we're in degree mode right now. So let's just go second tangent of negative 2 divided by 5. And I'm getting approximately negative 21.8 degrees. So alpha is approximately negative 21.8 degrees. Now, this is the most common mistake that I'm going to see on problems like this on a test. Because remember, in our theorem, actually before our theorem, in our definition of an angle of inclination, the angle of inclination is the positive angle the line forms with the x-axis in the closed interval from 0 to 180 degrees. So how do we convert this? Well, let's take a look at a negative 21.8 degree angle. And that's this quadrant 4 angle right here. But do you see that if I took that negative 21.8 degrees and I just added 180, that would give me this positive angle right there? So let's just add 180 to that. So negative 21.8 plus 180, and I'm getting 158.2 degrees. And there you go. To the nearest tenth of a degree, find the inclination of 2x plus 5y equals 15. Well, you're looking at it right here, 158.2 degrees. Okay, now we're going to do the application piece right now, all right? And you guys are kind of in a tougher situation here because, with our quarantine and COVID last year, you didn't get a lot of practice with conic sections. I think you probably only did circles, maybe, all right? So, again, I want you to take some good notes, ask some questions, and look over this with me. And seeing it for the first time, it might be a little abstract for you. But I'm going to try to go through this really slow. And I'm going to show you 2 ways to do these types of problems. And just have a little fun. Take it as a challenge. So, a conic section with center at the origin, whose equation has an xy term. So this b cannot equal 0 right here. You got to have an xy term. All right. Conic sections. First, conic sections. Well, a parabola is a conic section. An ellipse is a conic section. A hyperbola is a conic section. And a circle is a conic section. And, you know, you don't study those that much because most of them are not functions. All right? Right? But it's still really good stuff that you may need one day when you're a big-time engineer for Boeing or something like that. And trust me, when you are that big-time engineer, all right, Boeing's going to want exact answers. So there is no error introduced into problems, and the design of jets are not compromised. All right, notice I talk a lot about jets. They're kind of important to me. Anyway, let's have some fun here. Okay. Now, conics like this one may have one of their two axes inclined at an angle alpha to the x-axis. To find this direction angle alpha, use... All right, now, here's what they're saying right here. If there is not an xy term, if this b right here is 0, that means all of your conic sections are going to have a major axis and a minor axis that are always perpendicular to each other, and one will be horizontal and one will be vertical, which makes for some really pretty parabolas and hyperbolas and ellipses and even circles. All right. Now, if there is an xy term, that means we're going to have an angle alpha that's going to take our horizontal axis and rotate it. All right, so we don't have, you know, a horizontal and vertical axis. Okay, so let's play with this a little bit. And the formula is right here. A equals C implies alpha equals pi over 4. All right, simple enough. You see that in circles too a lot. And if A does not equal C, here's what we have to focus on. 0 is less than 2 times our alpha, and that has to be less than pi. And that will imply tangent of 2 times alpha will equal our b over a minus c. So with this general equation of a conic up here, all right, it is very, very easy to find the inclination of usually our major axis. It might be our minor axis. All right, so let's have some fun with this. All right. So, and again, yeah, wow, where's this going? Well, believe it or not, you're going to start graphing things like this down the road, all right? And, you know, again, we want beautiful graphs where we have our intercepts labeled and where this ellipse intersects both the major axis, which is the longer axis right here in the diagram, and then the minor axis right there. All right, and that angle alpha right there. Oh, this is going to be fun. And again, wouldn't it be great to be able to graph conics like this? So here we go. Identify the graph of x squared minus 2xy plus 3y squared equals 1. And that is a conic right there. And then find the direction angle alpha and sketch the curve. Okay, easy, right? Well, first, let me give you some simple rules for finding what kind of conic this is. All right. And I actually went to another textbook. All right. Because I want to do this. Classifying a conic from its general equation. All right. Now notice their general formula right here does not have an xy term. B is 0 here. All right. But this will still tell us whether or not we have a circle, a parabola, an ellipse, or a hyperbola. And it makes it pretty simple. So all I have to do is look. Does A equal C? Well, A is 1 and C is 3. No, so this is not a circle. And I'm down to parabola, ellipse, or hyperbola. And that's just based on what is A times C. So A times C, how does that compare to 0? Well, if A is 1 and C is 3, 1 times 3 would be greater than 0. And if A times C is greater than 0, I have to have an ellipse. So that part's simple, all right? It's going to be very easy for you guys to look at the general equation of a conic and tell me what kind of conic it is. Now, next, find the direction angle. Well, you have the theorem from the previous slide to find the direction angle now, all right? And here's my general conic right here. And you know, if B does not equal 0, then our conic has a direction angle. And here it is right here. When A does not equal C, which A is 1 and C is 3, then tangent of 2 alpha equals B over A minus C, meaning we're going to use this general equation right here to find our angle alpha, our direction angle. All right, so we're going to go tangent of 2 alpha equals, and I'm going to do this one more time general here, B over A minus C. And that equals, well, what's our B here? It's negative 2 over A1 minus C3, 1 minus 3. And hey, that looks like a negative 2 over a negative 2. That equals 1. I love it when tangent has an output of 1 because I already know tangent of any angle equals 1 implies that angle would have to be pi over 4. All right. So, hey, let's see if you guys can visualize that like that. Now remember this. Tangent is sine over cosine. So if tangent equals 1, then we'd have to have this quadrant 1 angle where sine and cosine have the same output. All right, and you guys know at pi over 4 or 45 degrees, both sine and cosine have outputs of what? That's right, root 2 over 2. So I already know that tangent of 2 alpha equals 1 implies 2 alpha would have to equal, and what are we in? Do they tell us anything here? No, so we could be in radians or degrees. I'm probably going to go radians here. How about I call this A? Yeah, radians, pi over 4. So if 2 times alpha equals pi over 4, then alpha equals what? Divide both sides by 2 now, pi over 8. So my direction angle is pi over 8, which I can already visualize right now. And that is likely the major axis of our ellipse right there. And now, what else do you know about the axes of conic sections? They have to be perpendicular. So that will be my minor axis, and that means for a rough sketch, I know that my conic is going to look something like this. And there's my rough sketch right there. Okay? All right? And look, we're almost there. All right? So, this is good, but I think we might want a little more detail. All right? So first, I'm going to show you how to get this graph using your calculator, which, by the way, won't be much better than this graph. And then we're going to do it without a calculator so you can find exact answers for things like our intercepts, or approximations might be fine too. All right? And where our ellipse intercepts both the major axis and the minor axis. And then we'll probably throw that direction angle into the picture too. So, method 1. All right? So this is using our graphing calculator. Graph of x squared minus 2xy plus 3y squared equals 1. All right, so if you're going to do this on a calculator, you've got to take this conic equation right here and put it in quadratic form and make your quadratic in terms of y so you can graph it. So, write as a quadratic in terms of y. That means our y is our variable, and we think of x as simply nothing more than a parameter really right here. So if I'm going to do a quadratic in terms of y, that means I need ay squared plus by plus c equals 0. So let's get there. So how many y squareds do we see up there? I see 3 of them. Okay? And then how many y's do we have? We have negative 2x times y, so this is a negative 2x. And then what's my c? Well, I need an equal 0, so see this 1 right here? let's subtract the 1 from both sides. So that would give me a c of x squared minus my 1. And in this situation right here, my quadratic, my a is 3, my b is negative 2x, and my c is x squared minus 1. Now, you're thinking, Gibbons, what are you going to do with this? Well, now we're going to use the quadratic formula, and the quadratic formula will give us a sketch of this ellipse. Okay, so there's the quadratic formula right here. It looks a little complicated right now, but we've got a lot going on right here. And you guys know the quadratic formula, y equals the opposite of b plus or minus the square root of b squared minus 4ac over 2a. So first, the opposite of b. What's my b? Well, it's this negative 2x. And then under the radical, let's take that b and square it. And then go minus 4 times a, which is 3, times c, which is the quantity, x squared minus 1, over 2 times a, and my a over there is still a 3. There it is right there. Now, I could put this into my calculator right now, all right, and get a sketch of this ellipse with a direction angle of pi over 8. But you know what? I'm going to clean it up a little bit first. So I'm going to say the opposite of negative 2x is 2x plus or minus, and let's square the negative 2x, and that would give us 4x squared. And then, see this negative 12 right here? Let's distribute that to the x squared. So I see a negative 12x squared. And then let's distribute the negative 12 to the negative 1 to get a plus 12. And over 2 times 3, which is 6. Hey, simpler already. And I think we can clean up this discriminant right here too. All right. By the way, the discriminant is another way to find out what kind of conic you have. All right. But we'll talk about that later. So the 2x, I'll leave alone. And right here, I can combine 4x squared minus 12x squared. So I'm going to write this as 12 minus 8x squared over 6. And that's about as simple as I can get this. And again, I could have put it in like I had it above, but it'd be really easy to make a mistake on my calculator if I did that. So now I'm going to get out my calculator, and I'm going to let y sub 1 equal this expression with the plus, and y sub 2 equal the same expression, except using the minus right here. So there's how I put that very, very carefully into my calculator, and I double checked everything. Doesn't that look good? And by the way, this looks way better than if I had done this right here. Right? It could be done, but I'm less likely to make a mistake on my calculator if I simplify first. All right, now we got to think, okay? What's this ellipse look like? Well, it's going to be centered at the origin, and it's going to have a direction angle of pi over 8. So what's my x and y window going to look like to get a really good picture of this? Well, I'll be honest, I played a little bit, and I came up with x's of negative 2 to 2, and I think I did the same thing with my y's. Yeah, just like that. So go to your window and go x min of negative 2, x max of 2, and I'd scale by 1s, and then a y min of negative 2, and a y max of 2, and let's scale our y's by 1s too. The rest of this stuff I'm not going to touch. And then I hit graph, and there's my ellipse right there. Isn't that beautiful? All right, so there is my calculator's version of the sketch of this ellipse, and I'm excited about that. Don't get me wrong, but remember what we already knew? There's our sketch we did by hand, all right? And yeah, I don't know, the calculator didn't give me much more. Now, by the way, I could find my intercepts right here on my calculator pretty easily, all right? But let's think about another method where we're going to do all of this by hand and then really fill in some really key points on this diagram right here. So, did the calculator give us any more than we already had? I really don't think so. So that's where method 2 comes in. All right, so we're going to graph x squared minus 2xy plus 3y squared equals 1. and we're going to do most of it by hand. All right, so here we go. Enjoy the ride. Now, we already know our direction angle is pi over 8, and we're going to use that to find the equations of the axes. Remember, this ellipse has a major axis right here and a minor axis right here, and they have to be perpendicular to each other. We also know it hasn't been translated horizontally or vertically, so our axis will intersect at the origin. All right, so slope. What is the slope of our major axis? Well, remember that m equals tangent of alpha. All right, can't we use that here? Can I say m sub 1, or the slope of this major axis right here? Wouldn't that have to equal tangent of my direction angle here, pi over 8? There you go. All right, so we're good to go here. So that is approximately, and I think we want to be in radian mode because that angle right there is in radian mode. So let's go mode, which I think we're in degrees. We are, and make sure you switch the radians, and please make sure you're punching this stuff out with me at home. So I'm going to get tangent of second pi divided by 8, and I'm getting 0.414213564. So I rounded that to 0.41. Okay? Now, 0.41. Well, if 0.41 is the slope of this major axis right here, and it goes through the origin, isn't the equation for that major axis going to be y equals 0.41 times x? Very cool. Now, there we go. Okay, let's find the slope of this minor axis right here. And they call them major axis and minor axis because they talk about just the part of this line that is within the ellipse. All right, and the longer segment would be a major axis, and the shorter segment would be a minor axis right there. So, what do you guys know about perpendiculars? Well, aren't perpendicular slopes negative reciprocals of one another? So that would imply m sub 2 would have to be the opposite of 1 over 0.41. Yeah, they're perpendicular, just like that. So let's punch this out. Negative 1 divided by 0.41. And I'm getting approximately, what, a negative 2.4? See if I rounded to the nearest tenth again. Okay, actually I rounded this to the 100th and this to the 10th, so it looks like I did, 2 sig digs on my slopes here. All right, anyway, negative 2.4 is the slope of this minor axis right there. So the equation then would be y sub 2 equals negative 2.4 times x. Okay, great. Now, what are we going to do with those two equations? Well, now it would be really easy to substitute to find out where this ellipse intersects with both the major axis and the minor axis. That would give me this quadrant 1 point right there, this quadrant 2 point, this quadrant 3 point, and this quadrant 4 point. So, yeah, I labeled those on the picture. And now let's find where the axes and the ellipse intersect. So there is my conic right here. And now, can I take the y's in this equation and substitute 0.41x for each y? So I'm going to make this y 0.41x and this y 0.41x, and I have to square that one. And now let's clean this up a little bit and solve for x. All right, so I'm at x squared minus, and I've got an x times x is an x squared and a 2 times 0.41. Would that be minus 0.82x squared? Oh, look at that. And then this one, I've got to square the 0.41, so let's go like this. On the calculator, go 3 parenthesis 0.41, and let's square the 0.41. All right, and that'll be my coefficient right there. which is 0.5043, and then don't forget the x's squared. So plus 0.5043 x squared. Okay, equals 1. Now, let's solve for x. And I'm excited because if I look at the left-hand side of this, every term is x squared. So that means if I factored out the x squared, I'd have to divide both sides by the coefficient of x squared on the left. So that means x squared would have to equal 1 divided by, and let's find out what that divisor would be. I'm going to use my calculator again, and I'm going to go 1 minus 0.82, and then a plus 0.5043. 0.5043. Double check that. 1 minus 0.82 plus 0.5043. And I'm getting 0.6843. So make sure you see what we did on that step. And yeah, I did skip a little bit there, but I'm trying to be somewhat efficient here. All right. So x then is going to be the square root of this funny expression, a fraction with a decimal. I don't really like that, but hey, it's the final results we're looking for here. So we're going to go, x then is approximately, and we're going to get a plus and a minus root. So let's go second square root of 1 divided by 0.6843, 0.6843. Okay. And I'm getting approximately like 1.21. And there's my positive and my negative right there. Beautiful. Okay. So those are my approximate x coordinates for this point and this point. So let's find our corresponding y coordinates, and again, to find those, let's just plug these x values into our y sub 1 is 0.41x right there. So let's go 1.2 times 0.41, and I'm getting a 0.492. How about I call that a 0.50? Yeah, that's what I did. And now the same thing with the negative, so that's going to be a negative 0.50 right there. Okay, good. Now I can label these points. So this would be my quadrant 1 point, which is right here. 1.2, 0.5. And this will be a quadrant 3 point, which is going to be right here. Oh, nice. Okay. Now, let's do the same thing to find this quadrant 2 point and this quadrant 4 point. And then we'll have almost a perfect graph. Note I said almost. So now we're going to substitute for y again, but we're going to use the equation or the expression for our minor axis, negative 2.4x. So these two y's right here become negative 2.4x's. Okay, now crunch a few numbers. So x squared, and let's see. Well, negative 2 times negative 2.4 would be positive 4.8. So the first term is going to be a plus 4.8 x squared. And this one, I better square the negative 2.4 and then multiply by 3. So let's just go 3 parenthesis negative 2.4 and square that. Okay, and I am getting a 17.28 x squared. Let's see how I did on my calculator. Calculator always scares me. If I'm going to make a mistake, it's when I put things in on my calculator, honestly. And now we'll do the same thing we did over here. Note, every term on the left has a common factor of x squared, so we would factor that out and then divide by its coefficient. So that means x squared would have to equal 1 over, and what is that coefficient on the left? Well, it would be a 1 plus 4.8 plus 17.28. Ooh. 1 plus 4.8 plus 17.28. And I'm getting a 23.08. Okay, now let's take the positive and negative root of this 1 over 23.08 to get x's approximately. So let's go second root of 1 divided by 23.08. And I am getting approximately 0.21. And the positive and negative roots, so that's going to be a plus or minus approximately 0.21. There it is. Now those are my x coordinates again for this quadrant 2 point and that quadrant 4 point. And you guys know what to do to find your corresponding y coordinates. Plug those two x values into our expression for our minor axis, negative 2.4x. So I'm going to take each of them and multiply it by negative 2.4. So negative 0.21 times negative 2.4, and I'm getting approximately, well, my calculator is 0.504. I probably call that a 0.50. There we go. And I know the other one would be the opposite of that, negative 0.50. And look at what I have now. This is a quadrant 2 point. And there it is. And this is my quadrant 4 point right there. And there it is. Now, isn't that picture becoming sweet? That's a lot of great information right there. Now, what would make this sketch perfect? And then I wouldn't even call it a sketch anymore. I would call it the perfect graph of x squared minus 2xy plus 3y squared equals 1. That would be, what are my two x-intercepts and my two y-intercepts? And that's just a little more arithmetic. So let's finish this thing out. All right. I blew this up a little bit with all the information we have. We have the equation of our major axis, our minor axis, and the 4 points where our ellipse intersects those two axes. All right. Well, I don't have this picture, and I should have this here. I put a little pi over 8 right there for a direction angle. Anyway, intercepts. Well, you guys are experts at x and y intercepts. What? At the y-intercept, x equals 0, and at the x-intercept, y equals 0. So let's do a little substitution right here. So note, I am finding my y-intercepts. Every x is a 0. And what do I have? 0, a 0. I have 3y squared equals 1. So y squared equals 1/3. So y equals plus or minus the square root of 1/3, which is y equals plus or minus root 3 over 3. Well, I just verbalized that whole thing. I guess I'm going to throw the little steps in here for you. So there's my y squared equals 1/3 implies y equals plus or minus the square root of 1/3, which I rationalized the divisor and wrote as root 3 over 3. All right, so that gives me my y-intercept on the positive y-axis and my y-intercept on the negative y-axis. There's my 0, root 3 over 3, and this point down here would be 0, negative root 3 over 3. Now let's do the same thing for our x-intercepts, and then I'd say we have the perfect graph. So now we need to let y equal 0, which leaves us, oh, look at this, x squared equals 1, so x equals plus or minus 1. That was easy. All right, so that means that this point right here would be negative 1, 0, and this point over here would be positive 1, 0. So there's my positive 1, 0, and there's my negative 1, 0 right there. And my friends, we are now looking at, beyond a sketch, we are looking at the perfect graph of the conic ellipse, x squared minus 2xy plus 3y squared equals 1. I hope you guys had as much fun as I had. All right, so let's see. What's this? More? What did I do here? Okay. Oh, I'm just showing off that picture again. Okay. And then I'm comparing it to the technology. All right. I don't know. If I'm an engineer, I'm way more into this baby right here. It tells me so much more. And again, we could use our calculator right now and find all of these important things, but it would have been a little work. I think it was a great experience to do this by hand like this. So I would like you guys to do the written exercises on page 299. That's 10, 12, 19, 23, 25, 27, 29, and 35. All right, and that's going to be mostly solving simple trigonometric equations, and make sure you know if your answers will be particular solutions or all solutions. and then finding the angle of inclination of a line. And who knows, maybe I'll throw a graph of one conic in there. I haven't decided yet. Let's find out. Okay, so you guys have a great day, and email me if you have any questions. Thanks so much.